Let's discuss the different types of block request. Whenever we try to access memory, we can do that in two ways. One is called as a single block request. So in a single block request, only one NVM block needs to be read or written in memory. It is usually used when the ECU is normally in running in a normal operation scenario. Examples are NVM read block, NVM write block, etc. So basically, the single block request is just used to access one block, and these kind of operations are usually used in a runtime. The other kind of block request is called as multi-block request. These multi-block requests are read but written in memory using multiple blocks, hence the name. Now, this is usually used in system startup shutdown kind of scenario, not in a normal running scenario. When the ECU wakes up or the ECU is going to sleep, that's when we use these multi-block requests, because it's something that uses a lot of resources. We can't have that happening every time. We can have it maybe at the start, maybe at the shutdown scenario. Now examples for these are NVM read all, NVM write all, etc. Let's look at the different synchronization mechanisms. See, the application software components use RAM block to read and write to NV block. So depending on how this data transfer is synchronized, so it's not like we can do this whenever we want at whatever time we want. This access should be synchronized. Otherwise, there can be corruption of data that can take place. So how do we synchronize? Depending on that, there are two types of synchronization. One is called implicit synchronization. The other is called explicit synchronization. Let's now discuss each of them. Implicit synchronization. So this synchronization is the most simple form of synchronization. Here we have a simultaneous access of RAM block is provided to both the NVM and the application. So both NVM and application have this concurrent access to the RAM block. So sharing of this RAM block between software components is not actually recommended in this case. Because for example, if there are multiple software components and they are accessing together the RAM block, then there can be some synchronization issues because there is concurrent access between NVM and the application at the same time. So it's not recommended to have this sharing of the RAM block between software components. And also, the application software components must ensure that the data consistency is there until NVM completes the operation. So, for example, the NVM is doing some operation, be it read or write. During this time, the application software components must ensure the data consistency. They should not modify the value at this particular time in the RAM block. So here you can see a simple diagram of how it is taken place. Like there is the RAM and then there is the NV block. So read write is basically done directly on the RAM block, and this can be done either by the application or the NVM concurrently. Let's look at the write request use case of implicit synchronization. Suppose we have just a single block request that we explained before. How does the steps takes place that we can look? So in case of implicit synchronization for a single block request, the application first updates the RAM block with relevant data. So the application first asks to update the RAM block with relevant data. Once that is done, it calls NVM write block or the NVM write PRAM block. The NVM write block API is called for a temporary RAM block, whereas the NVM write PRAM block is used for a permanent RAM block. So once this is called by application after the update of the RAM block, then NVM takes over. So that's all. In the application does its task, then NVM takes over. Now the application waits by either polling or using a synchronous callback. So application just simply waits for NVM's output or NVM status. So this status can be provided by either a polling mechanism where the application continuously reads or asks the status to the NVM, or it can be using an asynchronous callback. So this callback will be some API that will be called once the action or the process is completed by NVM. So once this NVM operation is completed, RAM block can be updated again. So once everything is done from NVM side, now a RAM block can be again updated by the application software component. Fairly simple, right? So that's the use case for a single block write request. Now let's look at the multi-block write use case. Here, for example, when the multi-block write request, as I told you, these kind of requests are used at the startup and shutdown. So the module that is involved here is the ECUM, which is the ECU mode manager. So it is the responsibility of ECUM to trigger this operations at the startup and the shutdown. So the ECU state manager, that is ECUM, calls the NVM write all API and transfer control to NVM. Okay, so that's the first thing ECUM state manager will do. When it's for example, in a shutdown case, ECU state manager first calls the NVM write all API. Now, like before, ECUM waits for NVM operation completion. Okay, by either polling or using a callback function. Very similar, like the previous case. First, the task is done. Like last time, it was application. Now it's ECUM. After the task is done, control is passed to NVM, and now ECUM waits for NVM's completion status by either polling or callback function. So that's all about the implicit synchronization part. Now let's look at the explicit synchronization. So in explicit synchronization, we have a concept of something called as a RAM mirror. Okay. So a RAM mirror is used to transfer data between RAM block and NV block. Okay. So previously we just had the NV block and RAM block directly. But now we have something called as RAM mirror, which is used to transfer the data between RAM block and NV block. So it's like a redundant, or what we can say, it's a copy of the RAM block, which is used to give this explicit kind of synchronization, which we are discussing now. So here, because we have an extra copy, we can actually employ the sharing of NVRAM blocks by different software components. Okay, because we are not all writing to the same block at this same time. That is the RAM block. Instead of RAM block, we have something called as RAM mirror also available. So because of that, now we have the opportunity to use multiple software component access. Figure shows a simple block diagram of how this is correlated. There is the RAM block, then there is the RAM mirror, and followed by NV block. So from the RAM mirror, we can actually be accessing RAM block. So RAM block can be updated and read bar written to RAM mirror. And then finally, the RAM mirror data is written to the NV block using read-write scenarios. In explicit synchronization, software components are responsible for copying the data that is consistent from the NVM module's RAM mirror using these APIs. That is read RAM block from NVM or write RAM block to NVM. It's the software component's responsibility to update the RAM mirror in a consistent fashion. Now this actually results in efficient use of RAM block. But everything doesn't give advantage, right? There's a disadvantage also here. The drawback here is the extra memory requirement. Okay, so because we have now one additional memory block which is used to store the RAM mirror, so this gives an additional overhead of extra memory requirement. The additional RAM block or the RAM mirror needs to have the same size as the largest RAM block that uses this mechanism. So there can be multiple RAM blocks, right? And there is the RAM mirror. So out of all these RAM blocks, which has the largest size, that is the size of the RAM mirror that is expected. Okay. Now let's discuss the explicit single block request and the multi-block request. Explicit synchronization write request, that's a single block write request. So here the application updates the RAM block with relevant data. Okay, that's the first step. It's very similar to previous case. Next, NVM write block or NVM write P RAM block is called by application. Now here is the interesting part. Application can still modify the RAM block till the API NVM write RAM block to NVM is called by NVM. Okay. So once the control is passed to NVM, still there is a period of time where we can actually modify the RAM block. And till when we can do this, till the NVM write RAM block to NVM is called by the NVM module. Okay. So that is the major difference you can see here. That some extra time we get even after writing to the RAM block. With this call, RAM block data is copied into RAM mirror. Okay. So finally, after this call, the RAM block data is copied to the RAM mirror. So if application just detects that there is some inconsistency, it can actually return e-note OK. So that will help NVM to understand that the data that is present is not consistent. So now if the NVM operation is completed, the RAM block can be updated again. Okay, so once this API NVM write RAM block to NVM is called, then application has to wait. And once NVM operation is completed, RAM block can be updated again. Let's look at the multi-block write request. So here again the ECUM module comes into picture. The ECU state manager ECUM calls the NVM write all API and transfer control to NVM. Okay, that's the first thing ECUM does. So if synchronization callback is configured, then NVM will call that. Application will have to provide the consistent copy of RAM block to NVM. And finally, if there is some consistency issue, we have to provide the e-note OK. Okay. And once all this is done, then the application can read or write to RAM block again. So here also ECM will have to wait for NVM operation completion by either the polling or the callback function. So only once that is done, we can actually go for the next updation. So let's summarize. The implicit synchronization we discussed provides a simple means of synchronization, with a drawback that the multiple software component access to RAM block is not recommended. In case of the explicit synchronization, it helps multiple software components update the RAM block, but with an increased demand for memory, that is the RAM mirror requirement. So depending on our requirement, we can actually select one of the synchronization mechanism and then proceed with that in the project.